Dear students, Assalamu alaikum. Welcome to this channel. Dear student, in the previous lecture we studied about Gauss's law, and today we are going to apply the Gauss's law to find the electric field intensity due to an infinite sheet of charge. But before applying Gauss's law, we must know some points how to apply that Gauss's law. Those points or those steps to apply Gauss's law, just keep them in mind. The first step is we have to assume a closed surface. Assume a closed surface. And this closed surface, we name this as Gaussian surface. This Gaussian surface is a closed surface. And what should be the shape of this closed surface? Yes, in the Gauss law, we observed that the electric flux to a closed surface that does not depend upon the shape of the closed surface. Hence, this closed surface, this Gaussian surface, may be of any shape, but it should be a symmetrical surface. And remember that this is an imaginary surface. This is not a real surface. This is an imaginary surface. This Gaussian surface is imaginary and it should be symmetrical so that we can calculate the area of that surface. And second point is point of observation. What is point of observation? The point where you are going to find out the electric field intensity. So the point of observation should lie on the surface. That should be on that Gaussian surface. And thirdly, the third point is find electric flux through that surface, through that closed surface, to the surface in terms of E, in terms of electric field. So these are the 3 points which we will be using for finding the electric field intensity due to an infinite sheet of charge. Okay, students, now we suppose that infinite sheet of charge. And remember that that sheet has certain conditions. That sheet is a thin sheet. That sheet which we are going to assume is non-conducting, and that sheet is infinite sheet. You know, in nature there is nothing, there is no thing as infinite in size. So we are just supposing it. This is a very large sheet, you can say that. And in this situation, we are just considering a part of that large sheet and we'll be solving over that. And then next thing is that over that sheet, the distribution of the charge should be uniform. Uniform distribution of charge should be on that sheet. So students, we assume a sheet, we consider a sheet. Let's suppose here we have a sheet, a thin sheet, and is of non-conducting material. As it is an infinite sheet, so we have considered a part of that sheet. And the charge is distributed uniformly over this sheet. Now students, if the distribution of the charge is uniform over a surface, then we define a term, we introduce a term, and that term is called surface charge density. And this surface charge density is in fact total charge on that sheet. If the charge is distributed uniformly over the surface, then whatever part you take, that would be the total charge on that, and over total area. So we represent this surface charge density by sigma. This is sigma. This is the surface charge density. So as this sheet has uniform distribution of charge, so its surface charge density is sigma, suppose. Now, the first step to apply Gauss's law is to assume a closed surface. So here we have a distribution of charge, and we are going to find out the electric field intensity near this infinite sheet of charge at a certain point. So I suppose a point, let's suppose this is the point where I'm going to find out the electric field intensity. So at this point P, suppose we are going to find out the electric field intensity, then we assume a closed surface in the form of a cylinder. So let's suppose this is the cylinder which is passing through the sheet, piercing through the sheet, and it is passed through the sheet in such a way that the part of the cylinder which is on the left side, that equal part of the cylinder should be on the right side of this sheet. So let's suppose the distance of this point P from the sheet is R, is I represent this. This distance is R, and the other face is also at the same distance from this sheet. These two distances are same. So this cylinder has two flat surfaces, and these two flat surfaces are at the same distance from this sheet. Now this is a cylinder, a symmetrical cylinder, and it has certain cross-sectional area. Let's suppose this is the area of cross-section of the cylinder of this flat surface, and here on the other side we have also the same area, and the distance is same. Now you know that for a positive charge, the electric field lines, they come out vertically outward. So all these electric field lines are emanating from this sheet outward. So some of the electric field lines are moving in this direction on this side, and some of the electric field lines are moving in this direction, emanating in this direction from this side. Now as the distance of the two flat surfaces of the cylinder is same from the sheet, so the magnitude of electric field will be same on these two flat surfaces. Secondly, the area of these two flat surfaces of this cylinder, that is also the same. So the flux passing through these two surfaces will be equal in magnitude. So I would write electric flux through both the flat surfaces is equal to, let's suppose I call that as phi 1, and this is equal to EA plus EA, and phi 1 is equal to 2EA. As you know that electric field is in this direction and the area vector is also in the same direction. Electric field if is in this direction and area vector for this flat surface is also in the same direction. So when you take the dot product of these two to find the electric flux, that becomes EA for this flat surface and EA for this flat surface. So these two flat surfaces, the electric flux through both the flat surfaces, that becomes 2EA. Now next is the electric flux through the curved surface of this cylinder, of this closed surface. Electric flux through the curved surface. This is, let me represent this by phi 2, and this is equal to 0. Why? Why this curved surface is not contributing in that electric flux? Because if we look at this surface from the front side, suppose, here I draw this. Let's suppose this is the flat surface. This is the sheet, and it was having a uniform distribution of charge. And let's suppose if the cylinder is passing through this sheet, then this becomes the situation. If you are looking at this sheet from the front side, this is the situation. This is the cylinder which is passing through this surface. Now over this curved surface, the area vector is always normal to this surface everywhere. Suppose these are the area vectors at every position, and the electric field line, as it is positively charged sheet, so electric field lines are coming towards you. These are the electric field lines, and area vector is perpendicular to that, so the angle between electric field and area vector becomes 90 degree. That makes electric flux is equal to 0. You can suppose in this way. Now this was the sheet and a cylinder was passing through this, and the cylinder is passed through this sheet in such a way that the two sides of the cylinder from the sheets are equal. Now this is the curved surface. Now if you look at this curved surface, from this curved surface, if this is the area vector and electric field lines coming towards you, then the angle between area vector and electric field becomes 90 degree. So the curved surface does not contribute in this electric flux, so it is equal to 0. So now we find the electric flux through the whole surface, whole Gaussian surface. This is equal to phi, and this phi is equal to phi 1 plus phi 2. So phi is equal to phi 1 is 2EA and phi 2 is 0. So electric flux is 2EA to this surface, and let me call this equation as equation 1. Now students, this is the electric flux to this whole surface, the Gaussian surface in the form of a cylinder. Next we apply Gauss's law to find the electric flux to this surface. Now according to Gauss's law, let me erase this. Now according to Gauss's law, electric flux through a closed surface is equal to 1 over epsilon naught times the total charge enclosed by that surface. Now we have to find out how much charge is enclosed by this Gaussian surface. For that, just look at this figure again. As this cylinder is passing through this sheet, so this cylinder is enclosing, suppose, this much charge. This cylinder is enclosing this much charge, and this cylinder was our closed surface. So it is enclosing this much charge. And how do we find that total charge enclosed? So this total charge enclosed by this surface, total charge enclosed, this is equal to, yes, sigma, the surface charge density, the charge per unit area, multiply the given area of this cylinder, the cross-sectional area of this cylinder, that is A. So this is total charge enclosed as sigma, charge per unit area, multiplied by the area, cross-sectional area of this closed surface. So this is total charge enclosed. So the above equation becomes phi is equal to 1 over epsilon naught into sigma A. You call this equation as 2. Now students, equation 1 is the electric flux through this closed surface by using the definition of electric flux E dot A, and this is the electric flux again through this closed surface by using the Gauss's law. Both are describing the same, both are telling about you the flux through this closed surface, so we can compare these two equations. So then we write comparing equation 1 and 2, comparing equations 1 and 2, that comes out to be 2EA, that was our equation 1, is equal to 1 over epsilon naught into sigma A. Now A and A cancels out. Why they cancel out? Because this was a Gaussian surface and that was an imaginary surface. So imagination goes out and reality is left behind. 2E is equal to sigma over epsilon naught, and E is equal to sigma over 2 epsilon naught. Now this is the formula for the electric field intensity near this infinite sheet of charge at this point. Vectorially, as electric field is a vector quantity, so we can write this electric field in vector form as sigma over 2 epsilon naught, as this is the magnitude. So to make this a vector, we multiply a unit vector r with it, so this becomes the electric field intensity near an infinite sheet of charge. So that's all for today. Here we have found the electric field intensity due to an infinite sheet of charge by using Gauss's law. Thank you.